All right, pre-calculus, we have been studying sequences. We've studied arithmetic sequences and geometric sequences, and I've hinted at this idea of adding the terms in a sequence together to produce what's called a series. So in this section 13.4, we're going to finally study the series. But first, before we do that, we have to study what's called summation notation. Sum means add, right? So a summation is adding things up. And this notation is also known as sigma notation. And it's called that because it uses this Greek letter S, which looks like that. It's a Greek S, a Greek capital S. And that stands for the word sum, meaning add. So summation notation is essentially a notation for adding up a bunch of things. And it uses what's called an index. And we're going to use the letter K to represent our index. The index is essentially a counter, just like we were using an index for the sequence terms. We talk about an. That subscript n is the index, and it counts which term you're talking about. We're going to use the same idea of an index, but we're going to use the letter k instead of n, because we're going to use the letter n as one of the limits of summation. So we have our index k. Beneath this Greek S, sigma, you're going to see k equals something, and often it'll be k equals 1. But it could be k equals 0 or 2 or 3 or whatever. That number is called the lower limit of the summation. And then at the top above the sigma, you'll see another number. That's called the upper limit. Often we'll use n, but sometimes it'll be like an actual constant like 5 or 10 or 20. That is the upper limit of summation. And then what we're summing up, the things we're adding are represented by sequence, so AK. So K is the index we're using for that sequence. So what this notation all means is you're going to take A1 plus A2 plus A3 plus, and so you're adding up the terms of a sequence, and you're going to add up all the way until you get to the nth term, AN. And so if this was a 5, you would only add up to the 5th term. If this was a 20, you would add up all the way to the 20th term. The fact that it says k equals 1, with a lower limit of summation equal to 1, means you start with A1. But if this said k equals 4 to 20 or something, you would start with A4 and add up to A20. So essentially the numbers that are below and above the sigma are telling you the first and the last terms in the sum. But then you have to add all the terms in between as well. Okay? Now usually in here, right there, you're going to put an explicit formula for the sequence, so that we know so that we can just plug in the numbers 1, 2, 3, 4, etc., so that we know what to add up. So let's do an example. So let's say you want to sum from k equals 1 to 5, k squared. All right, k squared, that is an explicit formula for a sequence in terms of k. It says start at 1 and go all the way up to 5. So what we're going to do is we're going to write 1 squared. That's A1. That's first term in the sequence, defined by k squared formula. And then plus 2 squared. That's the second term in the sequence, defined by the k squared formula. And then plus 3 squared and plus 4 squared. And we stop when we get to 5 squared. Boom. Done, because 5 is the upper limit of summation. And so now we've written it out. So this is our closed form, or not a closed form, but this is like a shorthand formula for saying add up all these numbers. And it's nice because if you have 200 things to add together, it's a pain to write them out. So you can write up the sum of that 200 things in a nice simple formula using this sigma notation. Now this, add them up and you get the value of this, which is 55. So if you actually say evaluate this expression given in sigma notation, it means figure out what this is equal to by adding these things up. Now sometimes we're going to do that the long way by actually adding everything like this. But I'm also going to show you some shorter shortcut formulas for evaluating and skipping this step in the middle and evaluating this more immediately, more directly. All right.